Hello all. In this video, we're going to look at the metrics that models use to optimize their task. So they're really an optimization problem. They're trying to build the optimal model that captures the data and performs the best. And so we'll talk about loss, which is the fundamental idea that relates to that optimization task. And then we'll also look at the tools that we use to figure out how well a machine learning model has performed. So we'll look at accuracy, precision, recall, and so forth. We'll also look at some tools for visualizing or summarizing the results from a machine learning model as well. Okay, so loss. What is this loss thing? Loss is a fancy word for error in a model. So with a machine learning system, they're given the inputs. Again, this is focusing on supervised learning. They're given the inputs, their examples, and the correct answers. And what they want to do is to minimize the variance, the difference between what the model would output and what the correct answer is. So they want to minimize loss, minimize error, minimize loss. So many machine learning algorithms, they are actually optimization algorithms. They're looking at minimizing the loss function. They use different loss functions depending on the task and the kind of data. And it's often built in, like it's kind of explicit with something like a neural network. You can see the loss changing as the machine learning model learns. With others, it's just sort of built into the nature of the algorithm itself. So if you have discrete outputs, it's like categorization, the loss function could really just count the differences, but that's not actually necessarily how it's done. They could be weighted in some way or another, or the outputs of the model may not be strict categories. They could be probabilities for different categories, and then we've got a bunch of different numbers that we want to combine. So one of the issues that we have when you start looking at loss is that the loss value is fundamentally dependent on the particularities of the data. And sometimes, like for classification with deep learning models, it depends on how many different categories you have and other qualities of the data. So it isn't always possible to say, well, if the loss drops to below point X, then we know we're done. It really varies depending on the model, and it's not something that you always think about. What we do want to see is that loss has decreased from maybe where it started at the beginning. There are so many different loss functions. I have a couple of links in here. This one in particular is an entry on Geeks for Geeks website, and it goes through the formulas for a number of different common loss functions, and then I'm going to go through some of them, but it'll probably have a slightly different set than mine. So let's just sort of start taking a look at different loss functions that are used. All right, first of all, cross entropy. This is the most common loss function used for classification problems. And in this instance, the version of the formula I'm showing here is for binary classification. So maybe you have dogs and cats, and you're just deciding between the two, and that's it. In that case, this formula would suffice. If you have more than two values, then you need to have a slightly more complicated formula. So what's going on here with cross entropy? Well, the value y here is the target value, and the log y of p, there we're looking at the predicted probability that a particular example is in this category. And so we have this formula that combines them together. It's called cross entropy. You don't really need to know the details, but if you want to learn more, the details are discussed on this entry for Geeks and other websites. Honestly, I recommend Wikipedia because the Wikipedia articles on these things are extremely detailed and very technical. All right, so when we actually use machine learning algorithms, sometimes we have to specify there are variations on cross entropy depending on the nature of the data. So if you have binary cross entropy with, say, a neural network, that implies certain things about the classification, like there might only be one output unit, one output number, which is going to be either 1 or 0. So there's a special form, this form of the formula for that case. When you have multi-valued classification, you use categorical cross entropy, and with the software that we're going to be using when we do deep learning later, there are actually two variations on that: categorical cross entropy and sparse categorical cross entropy. And the only difference is how the output is encoded. So it is common, the most common way to think about classification problems and outputs in neural networks is that the output is a one-hot vector. What does that mean? It comes from electronics. It means that we have, say, 5 categories. That means we will have 5 output units, a vector 5 long. For any given example, it has one category. So that one category will have a 1 in it, and all of the other entries in that vector will be 0. One hot means there's one non-zero entry in the vector. That's actually how this is implemented typically when you deal with neural networks, is that you want this sort of one hot representation. But when we actually store the data sets, we typically convert. So instead of giving it the vector with zeros and 1, 1, what we'll do is we'll specify the index where the 1 should be. So we'll have the target formatted as a number between 0 and n-1. The index in our array, in our vector, where it should be a 1, and all of the others are assumed to be 0. So as we get into later on, we'll get into deep learning. You should come back and look at this again, because it's really an important distinction when you're training to make sure that you're providing the correct targets for your model. All right, let's look at a few other loss functions for different kinds of problems. So hinge is a formula. You can see it here. It's looking at the target value for the output and the predicted value, and it's taking the largest of 1 minus the target or the predicted value or 0, making sure it doesn't have any negative outputs, and that is called the hinge function. It is particularly used for support vector machine learning, because support vector machines, their whole goal in life is to find a hyperplane through the data that maximizes the distance of that plane from any actual examples that it's seen. It wants to be like right down the middle, separating the data as widely as possible to avoid any errors that might come from things that are fairly close to the boundary between categories. Cosine similarity is another one. I don't have the formula right here, but it's used when we want to assess the similarity of two overall output vectors. So when you have an output vector, you can think about that output vector as a vector in multidimensional space. So we have two vectors that are pointing in different directions. The cosine similarity calculates essentially looks at the angle between them. So it has goes to 1 when they're pointing in the same direction, and when they're pointing away, it goes to the other extreme. It's very commonly used with text and evaluating text similarity. So you see this a lot in natural language processing. I have a couple other here. The mean absolute error. This is actually like the simplest kind of loss you could imagine. You just take your output values and you subtract them and you absolute value so you don't have any negatives, and you call that your loss. This works really well if you only have one output, but it doesn't work so well if your output is more complex in structure. It used to be really common for simple multi-layered perceptrons and other fully connected neural networks. It's not used so much anymore, but yeah, it exists. It's a more simple way of calculating loss. Regression problems will use mean squared error as that's like the base one, and then there are lots of variations. So it can use the square of the difference of each output and then takes the mean of those. So this is just a sampling. There are so many loss functions out there. And one of the things that professionals in the field will do, especially researchers, is they might experiment with coming up with a new loss function to see if that changes the learning of a particular model on particular data. And then they can explore for which examples it might actually provide some benefit. For those of us who are more practitioners or applied, where we're doing machine learning because we're interested in some other task, mostly you just use whatever's standard and then go from there. All right, how would you get your hands on the loss values? Well, many basic machine learning algorithms, it's not as meaningful a metric because it's intrinsic to how the thing operates, and it doesn't have like an iterative process where you could watch like over the training process, see the loss changing. You can ask some models where they're calculating the loss, you can actually ask them to report the loss at the end, if nothing else. So there are some ways of doing that if you have an algorithm that's doing this kind of iterative gradient descent process. We're going to use scikit-learn for the basic stuff. It doesn't really have a great way to get that information, although there are ways to get at that information. TensorFlow, which we're going to use for our deep learning on our in-class activities and the homework, it prints out loss automatically for us. So let's just take a look at what it looks like. So this is actually the output of a training of a deep learning model with TensorFlow. And you can, and we're going to get into how all of this works before. What I just want you to focus on is the statistics that it's printing at the end of each of these lines. So these are each step in our deep learning model's learning. It's reporting loss and accuracy, and then it's reporting validation loss and validation accuracy. The first two are those calculations for the training data, the data it's actually seeing and learning from. And then at the end of each step, at each epoch, it runs the validation data for you automatically and reports out those values. So you can see that the overall accuracy on the training data is 0.72, that's 72%, and the validation accuracy is 62%. So that's not bad. And the loss values, what we look at here is, are the loss values decreasing over time? They're generally heading downward, although not particularly fast in this case. So loss is very important for deep learning. It isn't as critical for other kinds of learning, like as something that you want to observe. But you can definitely ask a model or an algorithm to report out what the loss measure is that it's using. All right, the rest of these are metrics we use for analyzing how well the model is performing. Accuracy is a primary one. It's a simple one. It measures how well the model works. So it calculates the percentage of the instances or samples that you present to the model. What percentage of them did the correct answer be the result? And we'll talk about what that means for some of the different models as we go forward. I'm going to show you here the scikit-learn classification report. So this is something you can ask for pretty much any model that scikit-learn implements, which is a lot of them. There are literally hundreds of machine learning algorithms that produce different kinds of models. It's been developing for a long time, lots of different variations. This is actually it's showing a lot of different data. Accuracy is right here. So you can see with this particular training, the final accuracy was 60%. Probably that's on the training data itself. And then it has broken down other kinds of measures as well. And I want to talk through what each of these means. You may or may not report all of these for a given problem. You can choose which metrics you want to pay attention to. Accuracy is like the most basic one. You should be calculating accuracy if it makes sense for your problem. And then beyond that, you can add in these other measures because they capture different aspects of the problem. All right, so there are different pieces in this diagram. There's precision and recall. There's the F1 score. There's also this macro average and the weighted average. One of the things to notice is that precision and recall, as at a base level are calculated category by category. So in this case, we are training a model for classification. It has 3 different categories, 0, 1, and 2. And we have to calculate precision separately for each category, for each class. We do the same with recall. It's the same with F1. And then we have these cross-cutting averages of those others that you can also see. Hey there, this is Susan on Sunday, interrupting Susan from Saturday to redo a section. I apologize for this, but I went back and looked at my the segment of this video where I talk about precision and recall and realized that I kept misstating things. So I'm going to redo it and try to get it a little more accurate so that I don't add to confusion with what I say. All right, so we were talking about precision and recall as alternative metrics for evaluating models. Besides accuracy, precision and recall are also commonly used. They are looking for different things, and we calculate them slightly differently. So we're going to use this diagram, and I have another one which is specific. It has cats and dogs for us to actually look at. I want to explain this diagram first, and then we'll get into how precision and recall actually work. So this is a picture of the outcome of a model. It's been trained, it's doing okay, but not doing a great job. And so what you can see is the overall square is the space of examples, the space of our problem. And each dot is an example that we are training the model on. The dots on the left side that are shaded with green on the background, those are all dots that are meant to be positive. So we're treating this as binary classification. We have one where the answer is positive and one that is negative. You could think of this as being dogs versus cats. There's no value judgment associated here. We just tend to use positive and negative as a way of describing 2 different sets. So all of the dots that are in this green area should be positive. They should be given the category 1. And all of the dots that are on the left should be negative. What you can see is that the system that we've trained, the model that we've trained, is not completely 100% accurate. So inside this circle, the bright green circle on the left, those are true positives. So that means they are samples that are in our positive group, and the model correctly identified them as positive. On the left-hand side, we have true negatives in the area outside of the circle. Those true negatives, what that means is they are supposed to be negative, and the model categorized them as negative. So it gave the correct answer for the things outside of the circle on this side and the things inside the circle on the other. It gave the incorrect answer for the elements that are outside of this circle on the left, because those, it said, were negative, but they actually were meant to be positive. And it gave the incorrect answer for the values in the circle on the right, the red part, because those were meant to be negative. They're on the negative side, but it identified them as positive. So another way to view what's going on here is the model said that all the things inside this circle were positive and all the things outside the circle were negative. Okay, I think I've now said all of that correctly. Here's how we look at precision and recall. Precision is concerned about what proportion of the positive responses were correct. So it looks at the true positives and it divides by the total number of points that were identified as positive. I'm going to scroll my screen here so you can see here is a pictorial version of the formula for precision. It's taking the true positives and dividing it by all of the positives. So if you have something that has a high precision, then the true positives will be almost all of the elements that it identifies as positive. It will not have false positives. On the other hand, if it has low precision, which could happen because the model simply decides it's just always going to say positive, then you would have a situation where the true positives are a relatively small proportion of the overall positives, because it's just saying positive for a lot of other things. It's imprecise. It's not reserving that positive label for the ones that actually are positive. So that's precision. I'll note though that you can calculate the precision value for the positive category, and then you could flip it around and calculate precision for the negative category as well. And there we would be looking at the size of the true negatives divided by the total number of negatives that the system reported. So we can do the same calculation for either category, and we do. We're just focusing on the calculations for the positive because it's easier to draw the diagram skewed for that one and not for the other. All right, that's precision. Recall is more about how completely it's getting the correct values. So with recall, we are not concerned with the false positives or in fact the true negatives. We're really focused on the space of values that are supposed to be true. And we want to know what proportion of the values that are supposed to be true did the model actually identify as true. So we take the true positives and we divide it by the total number of positives in this right-hand region. And again, I'll scroll down a little bit and you can see there's a pictorial representation of the formula. True positives divided by all positives. So you can get a high recall value if you just say everything is positive. Then you will have no false negatives. Everything will get labeled that is supposed to be positive will be positive, and you'll get a really high recall value. Counterbalancing that, if you have a system that just says everything is positive, its precision is going to be very low because it will have a lot of false positives. So you can see that they are kind of measuring different things, and what we want is to combine them together in some way that makes sense. Now, before we move on to go look at those other metrics again, I do want to look at this. Also note the attribution here. I pulled this diagram from Wikipedia's page, and so this is a citation to it. And I'll note that there are a dozen different variations on this diagram. I don't know which one is the original one, so I just went with Wikipedia's because they tend to be pretty good about checking copyright. Also on the Wikipedia page was this diagram, which is just the same diagram, but where they actually used pictures to help us imagine what's going on. So the right-hand side here are dogs, the left-hand side are cats. In here we see the dogs that it correctly labeled as dogs. Out here we see the dogs that it incorrectly labeled as cats. We see the correct labeling of cats on the outside here, and the incorrect labeling of these as dogs are the section inside. Part of this diagram that's in my notes is the formulas that actually worked out. So for precision, we would look at 1, 2, 3, 4, 5 true positives, and we would divide that by 8 because we have 8 total positives that the model reported, and that would tell us the proportion of true positives we get out of what is labeled as positive. And for recall, we would look at 5 true positives and we would divide that by the total number of of dog examples, which is 12. There are other things that you can look at. You can look at the prevalence of dogs as a part of the data set. So 12 dogs out of 22. There are slightly more dogs than there are cats in this data set. And you can also look at accuracy, where you would look at the number of correct categorizations regardless of category and divide it by the total number. So here we have 5 true positives, 5 dogs that were correct, and there are 1, 2, 3, 4, 5, 6, 7 cats that are correctly identified as cats. So that's 5 plus 7 divided by 22 would give us the accuracy for this. I've included this in my notes so that you can take a look at it. And we also do have an attribution for this as well. Now we're going to go back and take a look at some of those other metrics like the F1, and we'll look at the closer again at the classification report that you get from scikit-learn. F1 combines together precision and recall. So we do the weighted harmonic mean. So 2 times precision times recall divided by precision plus recall. That's the F1 measure. It's a nice way of combining together the precision and recall values so that you get one number to look at instead of two, and it balances them together in a nice way. Accuracy we talked about. The macro average and the weighted average, they're relatively easy to understand. So each of these was calculated separately for each class. The macro average, this number 0.56, that's just the average, the straight up mean of these 3 values. So we average across the categories. We're treating each category equally. It doesn't matter if they have different representation in the data set. So it's possible I could have a data set where class 1 is half of the data and class 0 is another quarter and class 2 is another quarter. When we calculate the macro average, we just average their precision values, not paying any attention to how many instances there are in each side. The weighted average actually takes into account what proportion of the overall data each of these is. So it does a weighted average of these 3 values. All right, so the classification report, or these kind of reports, you'll see in a lot of papers on machine learning, and there are other measures as well depending on the task and the problem. I have a couple more things that I want to talk about in this video. The confusion matrix is one. This is a tool, in addition to like the classification report that just reports out some of those statistics for us, the confusion matrix can be really helpful when we want to analyze where the model is going wrong. So is there a pattern perhaps in which wrong answers it's giving? So a confusion matrix is a square matrix. It has a row for each category and a column for each category. And so I'm going to go to the example because I think that'll work just as well. So you can see that here we have our cats, dogs, and horses. So we're categorizing pictures into whether it's a picture of a cat or a dog or a horse. And so we have a row for the actual category, the targets that we have. So all of the pictures that were actually pictures of cats, they're going to be accounted for in the first row. And all of the pictures that were actually pictures of horses, they're going to be accounted for in the last row. Then we have the same categories, but as columns for the predicted values, what the model said that picture was. So a picture of an actual cat that was categorized as an actual cat, it would be added to the total here. So for this particular data set, we had 10 pictures of cats. 8 of them the model was able to accurately identify as cats, 1 it labeled as a dog, and 1 it labeled as a horse. Similarly, if we look at the dogs, there were 12 pictures of dogs. 10 of those the model correctly predicted were dogs. 2 of them it thought were cats. Notice that it did not confuse any actual dogs as being horses. And the same for the horse category. So when we draw this confusion matrix out, what we're often looking for is there a pattern in where it was going wrong? It's maybe interesting to us that the model did not have any confusion between dogs and horses, but it did have some confusion between dogs and cats. All right, the last topic I want to talk about is crossfold validation. This has been quite a tour of things. Crossfold validation is a common technique with standard machine learning. It is much less common for deep learning, and I'll talk a little bit about why later on once I finish explaining what it is. So the goal of crossfold validation is to ensure that we are getting as accurate a model as we possibly can. So the situation we're worrying about here is a situation where when we did the data, split the data into training and testing or training and validation, somehow it was askew. It wasn't representative. So maybe one particular category was really underrepresented in the training data and overrepresented in the validation data. Just by random chance. We're randomly choosing things for training and validation, but even randomness can do weird things, right? So you could have a situation where the split that you created was just bad and the model underperforms or overperforms or shows bizarre, strange performance. Crossfold validation helps us to avoid this, essentially by repeatedly training the model on different training and validation sets and looking for the overall trend. So if there's something, some split that's going to cause like a strange result, an anomalous result, we can see that and we can kind of wash it away. So how does this work? We are going to randomize the order of instances in the data set just to be sure. And then we're going to divide the data set into k equal sized chunks. So crossfold validation will sometimes actually call it like k-fold. Like the example, the picture I have here is 5-fold validation because we're dividing the data into 5 chunks. And then we repeatedly, for each 5 times, we're going to repeat pulling out a different chunk to be our validation data. And we're going to rerun the machine learning algorithm from scratch on the remaining data. And then we test and see what the results are. So here we are, where we have all of our data set. We have already split off a part to be our test data, and we're holding that in reserve. Now we're looking at what's left, and we're looking to split it into training and validation. So again, what we do is we divide that data into 5 equal-sized parts, and then we do different splits. So the first time we take fold 1 and we hold it back. The training data for this iteration will be 2, 3, 4, and 5. And then we'll test it with fold 1 as a validation. And then we're going to repeat the process. So we record all the statistics, the accuracy, the precision, the recall, all of that stuff. And then we do this all again. But we take the second chunk out and we train on folds 1, 3, 4, and 5. And then we use fold 2 as validation. And we record all of the accuracy and other measures that we want. And we do it again, where we hold back fold 3 as our validation set. And we train on the others. And we do it again, where we hold back fold 4 and we train again. And we just do this as many times as you like, or as many times as there are chunks of data. So you get to pick how many folds you want. But notice that what's necessary here is that the algorithm runs quickly enough that we can, in fact, rerun it at k times, 5 times in the case of this picture. And then we can look at the outcome across all of these and see which one has the most, is there a common value, right? Are they close to each other? Do they have close to the same accuracy, close to the same precision and recall? And that will tell us that that the model we're creating is actually valid. It's actually doing the same thing. There's not any peculiarities of how we split the data that are manipulating the results that we're getting. So that's cross-fold validation. I said we don't do this all that much with deep learning models. And the reason is that deep learning models take a really, really long time to train, like hours or days, or you need to be using exclusive, expensive, massive data centers, which are costly, to train more quickly. So it's expensive to train deep learning models. So it's often the case that we just don't do this cross-fold validation because running the model 5 times is just too much expense in time or money. We probably should actually do this, but it often does not happen. All right, so this is the end of our whirlwind tour of machine learning. I am going to do another video to add to this, which will go through some examples from what we're going to be doing in class with our activity. But hopefully this has given you a sense of the landscape. I don't expect you to master all of these terms. This is almost a reference for you, and there's just so much to learn in machine learning that what we'll do with it together is just scratching the surface, but hopefully setting you up so that you can learn more on your own as you go forward. All right, I'm going to stop there, and I will see you very soon.